All right. Thanks, Sonia. Thanks for keeping on me and making sure that I had my talk for this as I promised half a year ago. Um, all right, so I'm the last talk of the whole thing, so I'll try to keep it under an hour. Just kidding. Um, this will be probably quick and pretty high level, but what I'll be talking about today is kind of briefly going over some work I've been doing over the past few years on tensor networks and creating performance portable tensor networks. And what that has led to is a project that started this year about looking into how do we take these ideas where we have, all these the solver technology for tensor networks, um, and how do I start doing finite elements with that without starting to like write everything myself. Um, and then I'll last part of the talk I'll talk about current research, where we want to go with the project, and kind of just some early results. So this picture here in the top left is a picture of a whole realm, related to ICF. You guys may be aware of the National Ignition Facility. So you have these X-rays coming in, and it creates these hot spots on the surface, and those emit, radiation. And then you have this sphere in the center, and you have, forces impinging on that sphere. So being able to simulate that is important for fusion. Um, and to get it right, you need to part of the story is these thermal radiative transfer models. And so these are really complicated and difficult because um, at every point on your 3D grid, you're going to have an angular discretization, a unit sphere discretization pointing out in every direction. And then at every point there, you also have an energy grid discretization, and this is all evolving in time. So the state vector for these kind of problems are six-dimensional, and the PDEs are fairly complex as well. So trying to solve these is a huge problem, and these PDEs are part of the story of why we need such large supercomputers like El Capitan. So if you do a back of the envelope calculation of what kind of fidelity and resolution we wish we had, you would see it's a couple of orders of magnitude above even what El Capitan provides. Um, and if you just extrapolate this graph out linearly in semi-log terms, you would see that we're several decades away from getting what we need, assuming that'll be sufficient, and we won't find other hiccups along the way. But as you know, with Moore's law and the compute capacity of future supercomputers is a little uncertain. Um, that even just a linear extrapolation is probably too optimistic. So we really need to come up with other methods to try to bridge this gap and get several orders of magnitude more compute out of what we're doing. Um, so tensor networks could be one of the many solutions to this. You've heard of other things, I'm sure. But let me, in case you don't know what tensor networks are, let me give you a very surface level understanding of kind of what they are and how they can be helpful. So let's go back to finite difference, like we all learned in third grade. And imagine you have a grid where it's spatially varying in one direction, and it's constant in the other direction. So to store this grid would be, n squared. And if I want to compute a finite difference derivative on that, it would be n squared flops. Um, if you realize that you can store this as an outer product of two vectors, constant vector and then a spatially varying vector, it represents the same thing. And so in this form, in this storage sense, it's linear storage, so order n. And to compute the derivative, you only need to work with one of the vectors, so the flops are linear as well. And we don't even need the full gradient grid unless we want to visualize or something, or maybe we only need pieces of it. Um, so if we can keep everything in the form of the right-hand side of the page here in the low storage, low flops, this could be part of the solution to getting those extra orders of magnitude of effective compute. Um, so tensor networks are the generalization of this little cartoonish idea I just provided, where in each direction you have these cores, and they talk to each other through basically they have these ranks. So you can imagine like an SVD has several several vectors associated with it to reform the matrix, and you may end up not needing the amount of vectors that is needed to store the same amount of elements as the matrix. In that sense, you kind of have this multidimensional SVD-like thing, and if we can store the state vector as a tensor network, that could save us on memory, but then we have to be able to compute with that as well. There's a couple of different types of tensor networks. If you're curious about this area, I mean, there's lots of papers. It's becoming extremely popular. There's also there's tensor trains and Tucker decompositions. Um, I'll refer you to the literature if you want to learn more about the tensor networks themselves. Um, but what I've been doing over the past few years is working on this code called BoBa, where the idea is to create performance portable tensor networks. So it's going to be like Raja for tensor networks, in a sense. And so we start with the objects layer where we define tensors, vectors, and matrices, and the dense linear algebra and multilinear algebra on those objects. So, for example, we have backends for eigen or cuSolver or HipSolver, depending on what architecture you're running on. And if you're doing tensor contractions, we also have cuTensor, HipTensor. And the idea is that you can create your object and give it a compile time, for example, memory space, and it'll just do the right thing based on that option, and it'll handle all that for you. So you can write code that'll work on these various architectures efficiently. So once you build up these basic objects, you can then build up tensor cores. Um, and from there, once you kind of define this idea of a tensor core, you then have a tensor train. And then because everything kind of flows all the way to the back end, you hope all your operations that you define are efficient. For example, if you have a lot of tensor contractions, to define a tensor train multiply, then that'll be use the efficient contraction operations. You can also define, for example, tensor train matrices. So we have operators and the tensor trains are kind of like the vectors. So we have operators and vectors. So now we can actually start talking about discretizations and solving problems with those. So BoBa is all about creating the tensor network solvers that go into that are used to kind of solve like linear algebra problems. Um, so what does that have to do with anything? So if you say, okay, I care, we're interested in finding element discretizations, then BoBa doesn't know anything about spatial discretizations. So the idea is that, okay, where do we get that aspect of a full multi-physics solver? So, and for that, we're looking to use MFEM. And so that's what TensorFEM is. TensorFEM is taking BoBa and MFEM, getting them talking together, and so that we can create low rank solvers where all of the uh, finite element aspects of the solver are handled by MFEM, and all the tensor network aspects of the solver are handled by BoBa. Um, so I'll kind of explain some general structure and like a really kind of an example we have kind of working. Um, and then I'll kind of, in the next section, we'll talk about what we want to do with all this. So the first thing we did was say, okay, we need to represent functions in this framework. So you can define your finite element space just like you would. You could just pull a MFEM example and just start doing this. Um, you can define a function with a lambda that gives you a grid function. Then you can get the degrees of freedom from the grid function. And then with that, you can write that to a BoBa vector. So that's what TensorFim does is it takes a finite element space and a lambda and writes out the BoBa vector. When you can write these vectors, well, now I can start defining my tensor cores. Because tensor cores are again just like the vector, the 1D vectors. So I'm writing my function in terms of several the Carter products of 1D functions. I write those with the finite element space in mind. Um, I get the BoBa vector, and then I can put those together into a tensor train. So now I have my finite element method tensor train. Okay, well that's not enough. We need bilinear forms. So we can do the same idea. We have your integrators. Uh, they're put into your bilinear forms. From the bilinear form, we can extract the dense matrix, and we could put that into a BoBa matrix. Once you have that in BoBa matrices, you can then start forming tensor train matrices. So these are the operator side of what you're trying, your discretization or your solver. So interesting thing, you might say, okay, wait, dense matrices, that's a terrible idea. Turns out that for some systems that we've looked at, this is not true in general, probably. Uh, the the low rank dense matrices require the whole set of them requires less memory than the sparse full the sparse representation if you were doing assembling all the sparse entries of a matrix. So that was really interesting to see for some matrices of interest. Um, but it also lets you handle what if I want to do preconditioning such that uh, the preconditioner is low rank but and not sparse. So it's dense but low rank, and then so this framework can handle that kind of would be ideal for that kind of preconditioner. So it opens up a new uh, kind of paradigm in terms of what we could do for preconditioning. Um, so we can turn grid functions into these tensor train grid functions, bilinear forms, and do tensor train matrix bilinear forms. I'm still working on figuring out what to do with the meshes. Um, I have some interesting results or some very early results on transformations I'll show in a second. So what I'm doing is what I want to do is have the ability to have a mesh transformation, but I want to store the mesh transformation operator in this tensorized form, in a low rank form. So this example is I created a tensor train matrix with a transformed uh, sorry, is a tensor train matrix corresponding to a coordinate transformed operator. So that's a very small piece of the puzzle of what we want to do, and at the end I'll tell you where this is going. Um, but thinking about how to do that with meshes in a smarter way is definitely an interest of mine currently. Okay, so how do I put these pieces together for the thermal radiative transfer equations? So we use grid functions to create the spatial cores. We use bilinear forms to create the spatial operators. So this is for X and Y. But transport has also these angle discretizations, and those are collocation types. Currently, we're actually just writing those ourselves because those are easy operators to write. They're very straightforward, and they're basically just pulling from integration schemes and things like that. And sometimes they're just like constants or they're just identity operators or diagonal operators. Um, so you can actually mix and match, using MFEM for the spatial component and using something custom for the other components of your operators. So it's very general in that sense. Um, so this is currently what we're capable of running. So we're looking right now at the lattice problem. I'll refer you to the literature here on these. These are benchmarks created by Tom Bruner, um, and they test different aspects and robustness of your transport solver. Um, so the idea here is that this is a standard benchmark, so we're kind of going to run our solver over this, and so. On the left here is a sample solution using angular S6 angular quadrature. And if you're unfamiliar with this concept of the angular quadrature, I'd refer you to those papers, and they do a great job of explaining it. Um, so we're able to reproduce a result like this in TensorFEM. Our angular quadrature, I think, is picks different angles, so it doesn't look exactly the same. Um, but this was using just kind of explicit time stepping, so just applying the operator successively as a proof of concept to make sure we're getting things right. So this was a very exciting result to get. But really what we want to be doing is using implicit solvers who want to do implicit time stepping. So looking at TensorTrain GMRes or Amen, and then studying the compression rate, making sure we're maintaining a high compression rate. Otherwise, I mean, that's all point of this. If we're not doing that, then uh, we're not really getting an advantage here. Studying accuracy versus compression rate, because there is a trade-off space there. You can control the compression rate, and therefore, enter a trade-off space of uh, high compression rate, and that might have low error, low robustness, um, or you can have a lower compression rate and your result will be more like the untruncated result. Um, and you also we're interested in a block structured formulation. This will be interesting if you have either like multiple state vectors, or like a state vector it's not like just a scalar equation if it's a system of equations, but also if I want to do a spatially decomposed problem. So that isn't just a parallelism thing. In fact, in what we're looking at, for example, on each block of this lattice problem, we might want a tensor train per block. See, there's 49 blocks here if you think of this as a checkerboard. Um, and you might maximize compression by having local tensor trains instead of one global tensor train. Um, so figuring out how to do that in a sane way is also going to be interesting. Uh, maybe using the submesh capabilities or something like that. That's an area of future research. All right, so what are we currently doing? So you remember the ICF problem I showed you on the first slide? So here we have a 2D mock-up where we have these red lines are these small source regions, and then you have these thick walls and the thin region in the middle, and you have this spherical feature in the middle of the domain. So with tensor networks, it's frequently difficult to compress spherical features, because if you lay a circle on a Cartesian grid and you think of just like taking the SVD of that, it does not have a reduced representation. Um, so how could we get around that? Well, uh, this is kind of why I'm so interested in the coordinate transformed meshes. So if I take this circle and I re-represent it using this H mesh thing, so each of these blocks that are different colors are each a logically Cartesian grid. And I can write down the transformation analytically, and I can write down the inverse transformation analytically. Um, Unfortunately, it doesn't immediately exhibit a low rank structure, but if I sample things, you actually end up with a low rank structure on this grid. So that's a really interesting result that we got recently. That it's not like rank one, but it is a moderately low rank structure. These pieces can be represented in that way. But now the challenge is stitching them together, by creating the operators in such a way that we have consistency across the boundaries. Um, so there's another non-triviality here, and so the gradient operator for transport, the angles appear in front of the gradient operator in the free streaming term. So that means that they show up if we do coordinate transformations. We have this matrix here, this A matrix here in the middle. And so if we write out the new scalar equation, the coefficients in front of these derivative terms now have these four-dimensional functions. And uh, if you just think about if A11 was 1 and A21 was 0, then this would be really simple to tensorize and write in terms of Kronecker product structure. But A11 and A21 are functions of space, and there's no guarantee that the sign of this thing is constant on a domain. So I can show you that here. Um, this is just the value of the coefficient for a given angle, and you'll see that there are some places where there's a zero, and so that introduces a complexity in terms of writing things in Kronecker product because I can't just use an upwind operator or downwind operator globally. But for some pieces I can, but for different angles, that will not be true for different parts of these domains. So figuring out how to do that is something I'm currently working on. Uh, but another way to do that is to just kind of do like a naive thing and just create the full spatial loop over the number of angles and then create the operators completely in MFEM, extract them out, tensorize them on my side, and then you have tensorized coordinate transformed operators. But that process is really expensive, so coming up with a better way would be really good. All this is in collaboration. So the project I'm on is with Terry Hout. If any of you have worked with him, he's at Livermore as well, part of CharmNet. We also TensorFrame is being worked on also by Dmitry Anastratov and his student Max Hallett at NC State. In addition to that, we also have started a collaboration recently with the Allium code team at LANL. They're interested in porting their TRT code to use MFEM. So you may have seen some MRs um, for some of their work on the repo. Um, so I mean, while they're doing that, they're also interested in this tensor network research. So Zanio kind of caught a question from Ben randomly, and then uh, pointed him to the research that we just started, where we're going to be just looking at using TensorFEM to solve these problems. So for example, here this is the again the lattice problem. This is a different variation of the lattice problem, and this Larson multigroup on the famous MFEM star mesh. So obviously that will require a coordinate transform as well, just to get that right, but in the tensorized form. Um, yes, so that's all I have for you guys. I'm hoping next year to bring some really interesting results. Does anyone have any questions?
Thank you, Pierson, for this very interesting talk. Questions? Okay, maybe I can start. Are there any benefits from the tensor train representation with respect to GPUs?
So when we look at a tensor train MATVEC, a tensor train matrix core is a four tensor. So it's the left rank, the rows, the columns, and the right rank. So it's essentially a large stack of matrices. Whereas, essentially it's a stack of matrices the size of the number of ranks. Um, and when you apply that to a tensor train, the tensor train cores are ranks left, extent, and ranks right. So, the extents are going to match up with the columns. And what you can do is say, okay, that's a bunch of MATVECs. But really what it is, it's a tensor contraction. You're contracting the columns of each tensor train matrix core, the column extent to the uh, extent index of the tensor train, So doing that on GPUs uh, is step one, and then you have to permute them. So those are both two operations that are in the vendor libraries. And so there's huge advantages to huge accelerations to be gained from using GPUs for these operations because all of the efforts into AI has had these vendors really working on the efficiency of tensor contractions. So yeah, the idea is,
Any other
once we're
questions?
happy with our solvers, really kind of demonstrate how to do that on GPUs.